Chapter one, like I mentioned, is sort of a introduction to chemistry. We're not going to cover every single aspect of chapter one, but just a couple of things. Obviously, chemistry does sort of come across into a lot of different areas of our life. Everything from obviously medicine, energy, food, clothing, environment, all that involves chemistry at some point. You could be like a food scientist, for example, right? Seems like a good job. So it really does impact a lot of what we deal with, even in our everyday sort of existence, and we may not always think about it that way. But a lot of what we deal with in chemistry has to do with matter, and matter, as we will see, is pretty much anything that occupies space and has mass. So that's, pretty much everything for the most part. And a lot of what we deal with in chemistry has to do with matter, with really the different sort of states, for example, that matter may be in. And in terms of states, there's three common states of matter that we deal with. We have the solid state. And typically in the solid state, everybody is fairly well packed in there, pretty tight to one another, the atoms and molecules. That's why solids are pretty dense. They're hard to change the shape, as we'll talk about. Like, it's not so easy to fold this board up into something like that. And that, again, is because all the molecules and atoms are packed in there really, really tight to one another. Another state of matter that we commonly see things in is in the liquid state of matter. And in the liquid state, things are still relatively packed in pretty tight to one another. But there is a little bit more room for movement. And that's what I think about liquids. Liquids are fluid, right? You can pour them and stuff like that. And that's because the atoms, the molecules have enough energy to sort of pass one another. And they sort of have that fluid sort of characteristic that we do not see in solid, because they kind of lock themselves in place in solid. Nobody's really moving past one another, and that's why we don't see that there. Last state of matter is gas. And in the gas state of matter, that's the state of matter where everything has completely broken apart from one another. They're flying around, and as we'll talk about when we get to the gas chapter, as they're flying around, there's going to be collisions that occur. And as collisions occur, for example, with the container they may be in, that's what we associate pressure and gases and the pressure associated with gases from that. So a lot of what we deal with in chemistry deals with matter, the different states that this matter may be in, and also, how they perhaps transition from one state to the next. So for example, if we go from the solid state to the liquid state, that is the process known as, go for solid, liquid is, if I take an ice cube out of the freezers, will start to melt. Yeah, so that's the process of melting, and that's a good example of that, right? So as you go from, say, solid to liquid, that's the process of melting. If you take some liquid water and you're sad about your ice cube that melted and put it back into the freezer, that would be going from liquid back to a solid, and that is the process known as freezing. As we go from liquid to gas, that is what is known as evaporation or vaporization. And as we go from gas back to liquid, that is the process known as, anybody know? That is condensation. Yeah. So, like when you take a shower with the hot steam that's in there, hits the cold mirror, right? You get all that water that starts to develop on the mirror and all that. That is condensation. As we go from solid, for example, we could actually skip the whole liquid part of it. As I erase all my boxes, let me fix my boxes here. As we go from solid, skipping the liquid part of it and going directly into the gas phase, that is what is known as sublimation. And feels like I need one more arrow, so I'll do that. We could go from gas directly to the solid state. Once again, skipping the liquid state along the way. That is what is known as deposition, like you're depositing something, deposition. If you've seen it or remember it, now you could Google it, I suppose. DVD, CDs, yeah, they're kind of shiny things, and that's how they get them shiny. They do a deposition process, and it puts metals on them. I'm going to pass this around sign-in sheet, so we don't have to listen to me call his name, initial next to your name. All right. Now, a lot of these sort of changes of state is something very common that we come across in chemistry a lot of. In addition, does say the process here of melting and freezing, does that occur at the different temperatures, same temperatures? What do you think? Melting and freezing actually occur at the same temperature. And the same thing with evaporation or vaporization and condensation. They actually do occur at the exact same temperature. For example, this would be the normal melting point or freezing point. And this is the normal boiling point where that occurs. Now, for example, water, which is a very common example used for a lot of things, water 0 degrees Celsius is the normal melting point and boiling point. And for water, 100 degrees Celsius is the normal boiling point. Those two numbers are something you really should know as you go through your chemistry career. Those pop up a lot. So the boiling point and melting point or freezing point of water, 0 degrees, and 100 degrees are numbers that you do come across a lot. Now, what does that mean? It means, for example, with something like water at exactly 0 degrees, you basically have both phases happening at the same time. So you kind of have like sometimes referred to as like ice crystals. So you got a little bit of solid water at 0 degrees, and you got a little bit of liquid water sort of happening at 0 degrees, like slushy ice, if you want to think of it that way. So a little bit of water, liquid, a little bit of solid. It's not till you really get above 0 degrees Celsius, for example, that you really do fully transition into liquid. It's not till you're a little bit below 0 degrees Celsius that you actually would fully transition into solid. Same thing at the boiling point there. And by the way, at the surface of like any liquid, that's what's happening. You have liquid molecules that have enough energy to escape to go to gas, and some that will come back down into the liquid phase. So you got a little bit of both happening, not until you get above, again, 100 degrees Celsius in the case of water, that you really sort of transition fully into the gas phase, not until a little bit below that 100 degrees that you really transition into the liquid phase. So again, exactly at those, they're sometimes referred to as being in equilibrium with each other. And what that means is both phases are basically present at the same time, happening at the exact same time. And you may be wondering, so what determines sort of which way you go? That's another big part of chemistry, which is sort of the energy aspect of it. So a lot of times we do relate energy to a lot of things that we talk about. So for example, if we took something like solid to liquid to gas, would I need to put energy in to do those processes or take energy out to do those processes? What do you think? As it go from solid to liquid to gas, what has to do with energy? Should it go in or come out? That's both answers. So I'm assuming one of those should be the right answer, right? So we can actually take our ice cube example. It's a really good example of that, right? If you take an ice cube out of the freezer and put it like on the table. Now, maybe you have a pot of liquid water and you want to make some pasta, right? You put a fire underneath it right on the stove, start to heat it up, right? Putting energy in, and eventually it will start to boil, which is changing that liquid water into gas, right? At the boiling point. So all these processes, as we go from solid to gas, these are all processes where energy is absorbed. And in chemistry, when we talk about processes that basically will absorb energy, these are what are referred to as being endothermic processes. Now, as you probably can imagine, if we were going to sort of head in the opposite direction, we started at gas, wanted to go to liquid, and then go to solid. Those are all processes that require energy basically to be removed. So if you think about gas molecules, they're flying around really fast. If you remove energy from a fast moving gas molecule, it is going to slow down, frankly. It's not going to have as much energy when it comes in contact with other gas molecules. They no longer have enough energy to escape each other. So they kind of clump together, go into the liquid phase. If you continue to remove energy from that, they will continue to go into the solid phase, which is, oddly what's happening, right? When you take water and you put it into the freezer. Heat travels from hot to cold, right? Not cold to hot. So the hotter object gets colder object gets warmer. So when you put like a room temperature thing of water into the freezer, it's actually colder than the freezer's temperature, which means all the energy from the water you put in there is going to release to the freezer. That's why your water then will freeze, because it's releasing all this energy, and you'll make some ice cubes and stuff like that. So as we go from gas to liquid to solid, these are all processes where energy is released. And in chemistry, whenever energy is released, those are processes which are known as being exothermic. So obviously, a lot of what we deal with is matter. A lot of what we deal with is sort of these changes of matter, the energy component, and obviously we'll talk about really chemical reactions as well. And that's a lot of what we deal with chemistry here. Any questions on any of that there? So let's talk a little bit about one of the main aspects of chapter 1, which is sort of the idea of the scientific method and problem solving. Usually we want to think about some type of observation that we make, and that's usually the start of any type of experimental sort of process. You observe something that happens and you go, oh, that was interesting. Or you're working for somebody and they go, oh, that's quite interesting. Maybe you should go explore that. So when we observe something happening, a lot of times that will lead to what's referred to as a hypothesis. And a hypothesis is usually a testable sort of explanation of our observations. So a really good hypothesis is one where, you could do some type of experimentation, some type of testing to be able to maybe hopefully get those answers to why something is happening. You would then obviously do some type of experimental work. And unfortunately, a lot of times it ends up being sort of a cycle, if you will. You make these sort of observations, you come up with a hypothesis, you do some type of experiment, which oftentimes will lead to more observations, maybe some revision of hypothesis, more experimentation, and can be a sort of circle event, if you will. Hopefully at some point, it will lead usually to one of two things. It will usually lead to either a sort of theory or a law. And that's sort of the idea of what you're trying to achieve in this sort of scientific method. Yeah. So with these experimentations, again, eventually though, hopefully it will sort of jump out to some type of theory or some type of law, and we'll talk about here in just a second, sort of the difference between those two things. But ultimately, that's sort of the goal of these experimentations, and a lot of times that's what is sort of referred to also as the scientific method. And that's what we see here. So, what is sort of the difference between back here, a theory and a law? The idea behind this is hopefully we get to one of these. A theory, on one hand, is something that may on may over a period of time through further experimentations may be revisited, may be found to be incorrect, maybe in some aspects of it. So for example, there's Dalton's atomic theory, and Dalton's atomic theory, there's several points to it, as we'll talk about. There are several points that are correct still to this day. There are some parts of it that was found to be not so correct based on further experimentation. Something like Bohr's theory or model of the hydrogen atom works really well for hydrogen. But if you move past anybody other than hydrogen with more electrons, it really doesn't hold up. So the idea of a theory is, it really is sort of, you want to think about it, a tentative sort of explanation of what's happening. It's not really set in stone. There could be exceptions to that. It could be found that maybe in all aspects it's not correct. And that differs than what we see with a law. A law is a situation where no matter what the situation is, it always is going to basically happen that way. So the law of conservation of mass means, for example, in a chemical reaction, the only thing that happens is we break apart a bunch of bonds and we reassemble everybody on the other side. We don't change any elements as we start a chemical reaction and end a chemical reaction. So if we started with 6 carbons, we will end with 6 carbons in that chemical reaction. They may be in a different compound on the product side from where they started. But the idea of the law of conservation of mass is carbon's about 12 grams. So if we started with 6 of them, we will have the same 6 times 12 grams on the product side. We won't lose any mass along the way because we have that conservation of mass. And that always happens as well. Like the law of conservation of energy. We don't create nor destroy energy, but it can be transformed. Next. So when we have, for example, the classic example, potential energy, right? We got like a big giant boulder on the top of a hill that's about ready to fall off. It has a certain amount of potential energy based on its location. When it falls off, it transfers that energy to kinetic energy, which is the energy of motion as it goes through. When it transfers a bunch of energy to the ground, hopefully nobody's standing there, or transfers the energy to whoever's underneath the rock at that point. Don't lose really any energy along the way. It does go from one place to the next. So in chemistry, we think about it as sort of like a perfect sort of transfer of energy, if you will. If somebody gives off a certain amount of energy, somebody else will basically accept that same amount of energy. So it doesn't get lost. It doesn't go anywhere. It just can get transferred from one spot to next. So for example, if you lit a match or a Bunsen burner, that fire is going to give off energy, right? So that's giving off energy. The fire, the surroundings is picking up that energy that's giving off. So it is sort of that perfect transfer. We don't lose it. It goes from one place to the next. Just like if you threw a hot piece of metal into a cold cup of water, the metal will cool down, right? The water will heat up. Water heats up because it's picking up all the energy that the metal is losing, right? And that's why the metal gets colder in temperature, water gets hotter in temperature. There's sort of that perfect transfer of energy. So a theory is not necessarily set in stone, may not always happen in every situation the exact same way, could be found maybe not to be correct in all aspects. A law, though, is sort of locked into stone. It should always happen the same way every time along the way. Any questions on that there? Yeah. Truthfully, we measure energy with like a thermometer in a lot of cases. The change in temperature, right, is one way that you can measure the flow of energy. Temperature is basically a result, or temperature change is the result of energy either coming in or coming out. If something gains energy, right, we expect the temperature to go up. If somebody loses energy, temperature should go down. So in the case, if you wanted to, in that example, like I said, we'll actually talk about this when we get to that chapter. When you take that hot piece of metal and you throw it into the cup of water, if you just had a thermometer in the cup of water, you could do a very simple calculation to figure out how much energy the water gained. And because of the law of conservation of energy, you would know exactly how much energy that the metal lost to it. And so a very simple way to measure it is actually a thermometer and doing some simple calculations. Other questions? All right. So that's pretty much chapter 1. That was a good chapter. So I would say pretty much just a little bit about the scientific method there, laws, theories. Not too much out of chapter 1. So let's get into chapter 2, which is really the heart of what we're going to be talking about here to begin with, which is measurements. We're going to talk in this chapter how to take measurements, how to record measurements. We also talk about everybody's favorite things, which is scientific notation, also significant figures. We'll do conversions, and we will finish up, I think, with some density there at the back end of this chapter. So let's talk about measurements, and let's talk about really some important things that should always go with a measurement, and that is units. And whenever you make a measurement, record a measurement, in lecture, in lab, along your journey here through chemistry at Saddleback and outside of Saddleback, you should always record a unit. So why is a unit important? Let's just say, for example, I had 100. What do I have? 100 of? Any ideas? You have no clue because it's just a number, right? There's no unit to give you a frame of reference. I could have $100, which would be great, I think. Could have 100 apples. Might still be great if you like apples, I suppose. Could have 100 pennies, which is different, right? So a number by itself is pretty much useless, yes, in terms of science and chemistry. Whenever you take a measurement, it should always have two parts. It should always have a number and a unit associated with it. That way you have a reference of what that number means. It could even be something like 100 centimeters, maybe, is what I'm dealing with in this case. So always make sure that you write the number and the unit associated with it, so that you do not run into trouble and get a bunch of marks on your papers, for reality there. Now, there are two widely used system of units, sometimes referred to as the English system, which is what we use mostly here in the United States. And then pretty much everybody else rolls with the metric system for the most part. And you can imagine that obviously if people are using different sort of units, metric versus English sort of units, that could lead to some problems, especially obviously if you're doing business with people that use a metric and you're using English, there's going to be maybe some misunderstandings. So in 1960, believe it or not, they had a conference on weights and measures. Sounds like fun. And they came up with a sort of standardized system of units is sort of used for chemistry, for example, or science in general. And that is what is sometimes referred to as the SI system of units, or the International System of Units. So you'll oftentimes hear this is the SI unit or what the SI unit is. And it's sort of the standardized system of units that people in science use and usually in chemistry that we use. All intents purposes, it's pretty much the metric system. Yeah, so it's pretty much the metric system, which is what is used for the SI system. Now, when we look at some units here, it's also really important to understand what those units represent. And what I mean by that is, are you talking about a mass? Are you talking about a length? Are you talking about a volume? So the SI fundamental is the kilogram. For length, it is the meter. For time, it is the second. For temperature, it's a unit maybe you're not familiar with, but you will be at the end of this class, which is Kelvin. We also have a mole is a unit for sort of quantity. That's also sometimes used. So it's really important to understand what these units represent so that when you say, I have 5 volume, you have 100 grams, a mass, not volume. So you want to make sure that you understand what these units represent in terms of their measurement type. Yeah. It's a quantity of something like atoms or something like that. Yeah, it's quantity. So let's talk a little about some of these. Let's talk about length, volume, and mass. As I mentioned before, the SI unit there for length, which is sort of like a distance, is a meter. 1 meter is 39.37 inches. Commonly used units of length are meters, centimeters, kilometers, decimeters. I would say these are probably the big three that you will probably see for length, meters, centimeters, and kilometers. I don't know if decimeters will pop in all that much along the way, but it might. 1 centimeter is 0.01 meters. Or, just so you're familiar, if you divide 0.01 to both sides, 1 meter is 100 centimeters. So that's another way of looking at that. I would say definitely you should know that conversion. So whichever way you want to remember it, either like this or like this. If you like the bigger number, you might want that version of it. 1 kilometer is 1,000 meters. That's another conversion that you definitely should know. So make sure that you know definitely these two for sure along the way. As we talked about, I think on the first day, just a reminder that they do want you to be really prepared here. So we're not allowed to give you anything pretty much. So you do need to know these conversions as we talked about. So these are two very common sort of length conversions that are come up a lot in chemistry. Here are some prefixes, and sometimes we do use prefixes to change the meaning of a number, especially in the metric system. And these are a couple of common ways that you may see the prefixes given to you. I would say probably the most common way is like mega is 10 to the 6, for example, or centi is 10 to the minus 2. And these are probably the most common ways that you'll sort of see those prefixes. You do need to know these as well. You need to be able to kind of go from one prefix to the next. So this is a table similar to one in your book. So make sure that you do know that. But let's talk about how to properly use this. And it's probably used incorrectly by most people. So for example, if we say centi, like we had there, is 10 to the minus 2. So when we look at sort of a prefixed type prefix unit and like the base unit of what it is. So what I mean by that is, let's just look at centimeters and meters. That is the prefix unit. That is the base unit, right? The base unit there is meters in both cases. One is centimeters, one is meters. So when you go to a table like this and you see centi is 10 to the minus 2, that's how much there is in the base unit to one of the prefix units. So that is what that is basically how much in the base unit to one of the prefix units. So what that would mean is in 1 centimeter, there is 10 to the minus 2 meters. 10 to the minus 2 is really scientific notation. It is 1 times 10 to the minus 2. That is the same as we saw in decimal form of 0.01 meters. That's 10 to the minus 2, basically. Yeah. So I would say 90% of the people do it backwards. They'll go, there's 10 to the minus 2 centimeters in 1 meter, and do it backwards when they pull things off of this list. So you want to make sure that you do it correctly. It doesn't matter what the base unit is. If I had 1 centiliter, that would also mean I would have 10 to the minus 2 liters. So again, in one of the prefix units, there is 10 to the minus 2 of the base unit. In the case of centi, could be grams as well. If I had 1 centigram, that would be 10 to the minus 2 grams. So that's really important. It is a super common error that people make. They always want to flip these things around. So for example, here, why don't you try and fill this in correctly? Let's go with megagrams to grams. Let's do nanograms to grams. All right, so you fill it in. What should be on each side of that? Take a moment and see what you come up with. Use the little table there. Okay, so let's take a look. So we would go to this table, we would find mega, or we would know that mega is 10 to the 6th. So once again, that is how much there is in the base unit. So grams here is the base unit. So there should be 10 to the 6 or 1 times 10 to the 6 in scientific notation to 1 megagrams. If we go here to nano, which is here, it is 10 to the minus 9. And once again, that means that's how much there is in the base unit to one of the prefix units. So that would be 10 to the minus 9 grams in 1 nanogram. So again, super common. People always kind of reverse this backward. Once again, it doesn't matter. You would have, say, 1 nanoliter is 10 to the minus 9 liters. So it doesn't really matter what the base unit is. It is always how much is on the right there. Question on that there. So again, you need to know these. I would say along your chemistry journeys here, definitely mega comes up a lot. Kilo, centi, milli, micro, and nano. Again, deci, not too much, obviously, but since it's the only one left, you might as well throw it in there as well, I suppose. Yeah, so you do need to know these again, how to go from sort of the base unit, prefix unit. Any questions on that there? Okay. So let's talk about a ruler here, and this is the difference between our English system and our metric system. This is a conversion also that you should know. 1 inch is exactly 2.54 centimeters. This is your basic ruler. This is inches up on top. Yes, that is centimeters there on the bottom. What is all the little dashes on the very bottom scale represent when you look at a ruler? Anyone? So these are centimeters. Those are inches. Little guys are millimeters. Yeah, so the little guys are millimeters. There's 10 millimeters in a centimeter. So in case you look at a ruler, you know what you're looking at, hopefully. Again, inch. When you look at a traditional ruler. Now, the 1 inch is, again, a English sort of unit. And obviously centimeters falls under metric. So that's sort of the English to metric sort of difference between the two. So talk a little bit about volume and some of the units related to volume. Volume is the amount of three-dimensional space that's occupied by a substance. Volume is length cubed. The SI unit is actually meters cubed. So some common units of volume are some that we see on the bottom here. Definitely you should know this guy. That is used all over the place here in chemistry. Also this relationship here. So definitely should know these guys. 1 liter is 1,000 milliliters. And 1 cubic centimeter, which is what the CM3 stands for, 1 cubic centimeter is actually equal to a milliliter. It's a 1-to-1 conversion. So as we'll talk about, there's a few different ways that you could get a volume. One is, frankly, you could fill up a piece of glassware and take a volume reading. Another way is, for example, if you have some type of cube, you could take 3 length measurements, the length times the width times the height. And if you took each of these length measurements, say in centimeters times centimeters times centimeters, gives you your cubic centimeter. Now, your cubic centimeter is a volume. Each of these individual measurements are length measurements. So typically, especially with a cube, if you take a length measurement 3 ways and times it by each other, you will turn it into the volume. And that's a very common way that you could get the volume of an object, a solid object like a cube. We'll do it on Wednesday, actually. So you'll take some measurements there, length, width, and height, and that will get you your volume. So 1 cubic centimeter equals 1 milliliter. Sometimes cubic centimeter. It's also written as 1 cc. Like if you watch medical shows or something, right? Give the guy 5 cc's before they die. That is like basically 5 milliliters. So cc's is sometimes used in medicine as a version for milliliters, our cubic centimeters. So in chemistry, mostly we use cm cubed, not very much cc, but you may sometimes see it if it's sort of that application of it. So again, those two come up a lot. The 1,000 milliliters is 1 liter, or again, a cubic centimeter is basically the same thing as a milliliter. Now, mass is the quantity of matter that is present in an object. Matter, as we talked about earlier, is anything that occupies space. It's also a good idea to talk about there is a difference between the words mass and weight. Weight takes into account the force of gravity, mass does not. So usually in chemistry, we refer to whatever we weigh as the mass of the object, and you should do that as well, and not the weight of the object. The mass of the object, for example, will be the same here on the moon. Weight would be different as you have different forces of gravity. So very oftentimes confused by people because the process that we do to get the mass of an object is weighing, but we don't call it weight. We do call it mass. We do use this guy here. That's an electronic balance like we saw in the lab room, I think, the other day. We put it on there and we can get the mass of it directly. These, I think, are 3 big units of mass, are common units of mass that you should, again, know how to go between these types of units. Kilogram, a gram, and a milligram. There is, again, in 1 kilogram, 1,000 grams. There's also in 1 gram, 1,000 milligrams. So those are, again, 2 very common conversions that are used along the way. Really small units, so that's why there's a 1,000 of the grams in that case. So I definitely, again, would know these big 3 here along the way, so you know how to properly convert between them. So as I mentioned before, that difference between mass and weight, again, that difference of really the force of gravity. So you should get into the habit of referring to whatever you weigh as the mass of the object, and again, not the weight. Also really important, as I mentioned earlier, to make sure that you do understand what those units represent. So if you weigh something, you're not saying I got 50 grams of volume or anything like that. Again, that would be a mass. So let's talk about temperature conversions and how we convert between the different scales. And really, there are 3 temperature scales that we come across in chemistry. There are degree Fahrenheit, degrees Celsius, and our friend Kelvin. Now, one of the major differences, as you can see, the way I said it and the way I wrote each of these is we do not use the degree sign there for Kelvin. So it is just Kelvin. So if you had like 273 Kelvin, that's how you would write it. You wouldn't put degrees Kelvin. You do use the degree sign between Fahrenheit and Celsius. Now, on the Fahrenheit scale, that's what we use for like body temperature. We have water boiling at 212 degrees Fahrenheit. 32 degrees Fahrenheit is freezing. Or if you're at the Buffalo Bills game, I guess it's below freezing, that temperature there. Celsius, 100 degrees Celsius is the boiling point for water. 0 degrees Celsius is the boiling point for, 0 degrees Celsius is the melting point or freezing point for water. Those 2 numbers you should know for water. It comes up a lot in chemistry. So, and we do use it in Celsius is pretty much the version for the most part. So 100 degrees Celsius, boiling point for water, 0 degrees Celsius, freezing point for water. Those 2, again, for water come up a lot. I would say the third temperature scale, which used to be called the absolute temperature scale, was later renamed for Kelvin. Water boils at 373 Kelvin and freezes at 273 Kelvin. Out of these three temperature scales, for the most part, outside of chapter 2, you probably won't see too much Fahrenheit pop up along the way. I will say usually temperatures are given to you in Celsius in chemistry. And for the most part, 99%, even more maybe, of all chemistry type formulas and equations require the Celsius to be converted to Kelvin. So it's a pretty safe bet that if you're doing any type of chemistry type of calculation, you have temperature involved, probably the first thing that you should do is convert that thing into Kelvin, because pretty much every equation requires it to be in Kelvin. We're going to talk about how to do that in just a second. So how do we convert between these? Really, the way that we convert between these have to do with the differences between where water boils and freezes on each of these scales. On the Fahrenheit scale, it's about a $1.80 difference, and it's about 100 difference on the other scales between where they boil and freeze. And that's the basis of how we do these conversions. That's what we see here. Again, about 180-degree difference there on the Fahrenheit scale, 100 difference on the Kelvin and Celsius scale. So here are our formulas to convert between each of these things. I will say the first one is the most important, and I'm going to do an adjustment here as I was told to do. If you have the, we'll put it in there. If you have the temperature in Celsius and you want to convert it to Kelvin, you're going to take the temperature in Celsius. You're going to add 273.15. As I might have mentioned the first day, they want you to use the 0.15, so we will teach it. So 273.15 is the real number. I will say that some teachers will want you to use 273.2, which is kind of like what it is in a lot of the lab experiments. So you'll see 273.2 or 273.15. The true real number is 273.15, so we'll roll with that number, even though it's going to get rounded off anyways. All right, so we'll keep it. And that conversion right there, you 100% need to know. And I would say 99% of the time outside of chapter 2, that is what you're going to be doing. You're going to be taking the temperature in Celsius and converting it to Kelvin. Now, sometimes you do need to go from Kelvin back to Celsius. So to do that, we would actually be subtracting the 273. So we will go the temperature in Celsius would be the temperature in Kelvin minus 273.15. So these two here, I would say, will probably make up the majority of your temperature conversions. But in this chapter, and occasionally you may have to do some other conversions. So let's talk about how you go from Celsius to Fahrenheit. Temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus a 32. So 1.8 temperature in Celsius plus a 32. If we want the temperature in Celsius, we're going to subtract 32 to the other side, which will give us the temperature in Fahrenheit minus 32, and then we're going to divide by 1.8. Now, 1.8 is that 180-degree difference between melting and freezing. You may have learned as well, it's 9/5, same conversion. So if 9/5 is sometimes used by people, which will give you that 1.8. Now, if you need to go from Fahrenheit to Kelvin, you got to take it from Fahrenheit to Celsius and then Celsius to Kelvin. And same thing, if you're starting at Kelvin, you go all the way to Fahrenheit, you got to go Kelvin to Celsius to Fahrenheit along the way. Once again, probably outside of 2, not going to be referencing probably those bottom 2 very much. You still should know it. You're still responsible to know it. Again, the top 2 there, converting Celsius to Kelvin and Kelvin back to Celsius, are the 2 very common conversions that you do. Now, let's take a look at some here. So why don't you grab your calculator, make sure it all works. And let's try these 3. Temperature is 28.5 degrees Celsius. What is it in Kelvin? We got 41 degrees Celsius. What is it in Fahrenheit? And 160 degrees Celsius. What is it in Celsius? So take a moment there and see what you come up with. Okay, let's take a look, see how you're doing. So here on the first one, we are going from Celsius to Kelvin. So again, our temperature in Kelvin equals 273.15 plus our temperature in Celsius. So we'll plug that in there. Temperature in Kelvin equals 273.15 plus our 28.5. And we will end up with 301.65. Again, this is going to be Kelvin, no degrees Kelvin. Now, in terms of when we are doing temperature conversions like we are doing here, and you're only doing temperature conversions, basically converting a temperature value from one scale to the next, we actually follow a little bit different rules than we do when we do like normal calculations in terms of like significant figures. So because people could use 9/5, 1.8, 1.80, there's a lot of variations in terms of the formulas there to do conversions for temperatures. So the basic rule of when you are simply just doing a temperature conversion from one unit to the next, you make your answer look like the original number. And what I mean by that is the original number here went to one decimal place. So we would actually take this here to just one decimal place. If our original number was a whole number, we would take it to a whole number and so forth. Went to two decimal places, our original number, we would take it to two. So that is specific. It does not follow strict significant figure rules, as we'll talk about, but that is specific just for temperature to temperature conversions. We would. So it's a good question. In this case, we would look at that 5 and normal rounding rules apply. So, 5 and above, we just round up, right? If it's less than that, then we just kind of drop whatever's after that. So in this particular case, we would round this to 301.7 Kelvin in this particular case. Any questions on that there? Yeah. Would it be, I'm not sure I understand. Would it be specified how far to take the answer? Is that what you're asking, or? It doesn't. So in all answers, you should always round to the proper number of significant figures. Uh, Again, for temperature conversions here, temperature to temperature conversions, we don't follow strict significant figure rules. So we do follow that general rule of whatever the original number looked like, that's what the converted number should look like. So in this case, since the original was one decimal place, that part of the problem would tell us that we should take our answer to one decimal place. But it will not specifically say, hey, take it to one decimal place or something like that. We will talk about it in a few slides down the road, but it's really the important numbers when you take some type of measurement is basically what those are. It would be in this particular case. And again, this type of conversion doesn't follow really strict significant figure rules. We're going to talk about rules when we do calculations shortly in this chapter, but that's just the general rule that you want to follow here. Yeah. The answer that you should give is what's in the box, which is this original number was one decimal place. This one went to one decimal place. That's what and you should round. Yeah. Other questions? All right, let's take a look at the next one, which is Celsius to Fahrenheit. So our temperature in Fahrenheit will equal 1.8. Our temperature in Celsius plus a 32. We're going to go 1.8, 41 plus 32 in this case. So 1.8, maybe put 1.8, there we go, times 41 plus a 32. Going to go 105.8 is what you get on your calculator there. This would be degrees Fahrenheit. Once again, here I should take this to 106. Once again, our original number was a whole number. So that would take us to here. Again, with the 8, we would round up and we would end at 106 degrees Fahrenheit. Question on that there. All right, looking at the last one, we have Fahrenheit wants Celsius. So temperature in Celsius going to be our temperature in Fahrenheit minus 32 divided by 1.8. That's going to give us a 160 minus 32, 1.8 dividing. So we're going to take 160, we're going to minus 32, going to hit equals divided by 1.8, or 18 if you miss the decimal. 1.8, that's better. And that's going to give you on your calculator 71.111, a bunch of ones. In this case, once again, we should take it to, this is a whole number, which means we actually should end up here at the whole number in this conversion. Since that is all we are doing, it's just a temperature conversion. So we would take it to 71 degrees Celsius. So once again, this specific rules strictly for temperature to temperature conversion. That's all you're doing. You make the converted number look like the original number. There's different rules, obviously, when we do different calculations that we will talk about as we go through this chapter. Yeah. No, it is strictly the rule here that it actually is looking more at it's a whole number. Yeah, in this case, yeah. And just as we will talk about, zeros can be significant as well. So we'll talk about, yeah. Other questions? Okay. And again, strict rules just for temperature conversions. We'll talk about the more specific rules for significant figures as we continue on in this chapter. Exactly. Yeah. Don't overthink it. Yeah. It goes to one decimal place. Give your answer to one decimal place. If it's a whole number, two decimal places too. And again, just for temperature to temperature conversions. All right. So let's take a look at these and let's talk about the different types of measurements we got going on here. So Kelvin should be a measurement of temperature. Yeah. Liters should be a measurement of volume, right? Meters should be a measurement of length. And kilograms should be a measurement of mass, right? So again, it's really important to understand what those units represent in terms of what type of calculation that you are dealing with. It just makes your life easier in the sense that you're saying things correctly, but more importantly, when you start intermingling sort of formulas with that, you know, when you see a number, oh, that's the volume, I should use it here, or that's the mass, I should use it here. So again, really important to have that understanding of what those things represent. Let's talk about a couple of different types of observations, qualitative versus quantitative. Qualitative consists of general observations about a system. It's pink, turned purple, there's polka dots, unicorns came, I don't know, whatever it may be. Just sort of general observations. Qualitative is really does not involve measurements. If you continue on in chemistry to 1B, you do a bunch of labs, smelly labs, that involve what are known as qualitative analysis, which is pretty much in the laboratory. You don't measure anything. You do like 40 drops is kind of about right. 20 drops, you know, a little small scoop of this, not measuring out masses. So there's actually a whole bunch of experiments that you'll do when you get to 1B, which are qualitative in nature. You never take anything out to measure, basically. You just, you know, sort of eyeball it and stuff like that. And that's different than a quantitative sort of measurement. And pretty much like it says, a quantitative observation is really a measurement. It consists of taking measurements. It consists of numbers, units, something that you measured. So when you take something to the balance to weigh it, you should do that quantitatively. You should get the exact mass that it weighs, not like the scale says 50.352 grams and you go, yeah, 50 sounds about right, and just record 50. So you want to record exactly what's in there. Quantitatively, if you measure out something, pour something, you need 5 milliliters. You want to make sure that you measure exactly 5 milliliters and stuff like that. So quantitative is measurements revolving units and numbers and values. Qualitative, more general, just sort of what's going on. Maybe there was fire that happened, or smoke, or a solid formed, or something of that nature. So let's talk about one way that we write numbers in chemistry, which is really important, and that is what is known as scientific notation. And scientific notation has a general formula of something like this: n times 10 to the n. This first n is a number between 1 and 10. So it's not 10, it's not 20, it's not 100. It's actually not less than 1. It's not like point something. It needs to be a number between 1 and 10, but not 10. So before 10. And the next one is times 10 to this little n, which is a positive or negative number. And that really depends on which way you need to move the decimal place to get to a number between 1 and 10. So maybe sort of positive moving or negative moving. And we use that, for example, 1 gram of hydrogen is 602.2000000. I lost how many zeros at this point, but there's a, use the right word there. There's a lot. I'll just go with that word. That seems like a safe word. There's a lot of zeros in that number there, and you probably would lose some of those zeros along the way if you had to rewrite it, use it in a calculation. Same thing here. This is the 0.0000, a bunch of zeros. And obviously, if you use that number the way it is, you probably are going to lose some zeros along the way. By the way, first number is a really large number, right? Second number is a really small number. And when you write something that's a small number, it is also really important to keep that 0 in front of the decimal when you write it, and not just write it like this. And that's because when you do a bunch of calculations, all of a sudden these numbers will start to run together. So it's really important also when you write a small number in chemistry that you do put that 0 before the point, so that it's very clear what number goes with which and things don't run together. So we do use scientific notation to help us do that. So if I had a number like 125, there's no decimal written, but we do assume that it's sort of at the end here. We would need to go one place to the left. That would give me 12.5, which is not between 1 and 10. So I do need to go one more place. That will give me 1.25, which is a number between 1 and 10. So 1.25 times 10 to the 2. It is positive number. The number is how many places I move to get to that number between 1 and 10. And it's positive because I moved to the left. If you want to remember it, positive exponent for large numbers. Yeah, so large numbers over 1. Yeah, we'll have a positive exponent. Now, if I had something like 0.00234, I would need to go one place, not between 1 and 10. One more place, not between 1 and 10. One more place does give me a number between 1 and 10. And that gives me 2.34 times 10, 1, 2, and 3. This would actually be negative because we move to the right and it's a smaller number. So if you want to remember it like that, if it's a number less than 1, it should have a negative exponent as well. By the way, I kept all those numbers because, as we will talk about, they are all significant, which means when you write a number in scientific notation, you should not lose any significant figures along the way. And when we talk about significant figures, any of the numbers that come before its 10 part, when you write a number in scientific notation, they are always significant. So for example, this one here would have 3 significant figures. This one here would also have 3 significant figures. If I wrote something like this, 1.2 times 10 to the 4, it would have how many significant figures? It would have 2 significant figures. Yeah. By the way, if I needed to turn that into a decimal form or positional notation, I would need to take the 1.2 and move the decimal place this way, right? Because it's a positive, so it should be a larger number, and put zeros in there. And that would give me something maybe like that. Yes. If we have to go the other way. Yeah. Question on that there. So it's really important to be able to write numbers in scientific notation. Also go for scientific notation to decimal form. The question is perhaps, do you need to give all answers in scientific notation? For me, you do not need to do that. You do have to give all the answers to the proper number of significant figures. And I will say, as we go through this chapter, there is sometimes the only way that you could give the right number of significant figures for an answer is to actually write it in scientific notation. So sometimes the only way you could actually give that number properly to the right number of significant figures is to actually put it in scientific notation. The nice thing about scientific notation is you can control how many significant figures you need. So for example, this guy has 2. Let's say I need a 3. All I have to do is go 1.20 times 10 to the 4. Now I have 3 significant figures, right? If I just needed 1, I could do 1 times 10 to the 4. I would have 1 significant figure. So with scientific notation, you can kind of control how many significant figures you would put in an answer. And like I said before, sometimes that is the only way to achieve the correct number of significant figures, which is what you want to always do in your calculations. Obviously, if the problem says give the answer in scientific notation, then clearly you need to give it in scientific notation. But if it doesn't, you could give it in decimal form or scientific notation as long as the right sig figs, which we'll obviously talk about the rules shortly. Yeah. Are you talking about like the 1.20, the 1.2? Is that so? As we will go through a few more slides down the road, probably next time as well, but we will talk about the rules for significant figures, and that's really what's going to determine which one you should give up. So if you did a calculation where you look at the calculation, which is what you'll have to do and go, oh, based on this calculation, I should end up with 2 significant figures, then you would want to go with like the 1.2 times 10 to the 4. Or if you did the calculation, go, oh, I should end up with 3 significant figures, then 1.20. So it would be based on the actual calculation that you're doing at that point, unless it just specifically gave you a number and said, hey, write it to 2 significant figures or something like that. Other questions? Yeah. So there's that. There's that. All right. So let's talk a little bit more importantly in this last 5 minutes or so that we got. Let's talk about scientific notation and your calculator and how to properly punch it into your calculator, which I find most people do not know how to do. So let's talk about how to do that. Every calculator that's a scientific calculator actually has an exponent button, and on your calculator, it may say EE, it may say EXP, or if you have some of the newer calculators, I guess they're not new these days, but they were relatively new several years ago, kind of like a 2-tone calculator. You may have a button that is like times 10 to the n. And usually on those calculators, you will also have like a little wheel or something like that next to it towards the top right of your calculator. So if you have these two, we'll talk about how to do that. If you have this type of calculator, we'll talk about how to punch it in there. But usually that will take care of pretty much most people's exponent button. I would say 90% of the time, the exponent button kind of mid-left of your calculator or bottom right is where those buttons are. So let's say we wanted to put into our calculator something like that, 1.25 times 10 to the minus 4. The proper way to do it is you would take 1.25. You will then hit your exponent button, either your EE button, your EXP button, whichever one you got. And depending on your calculator, probably one of 2 things will pop up on your screen. It will say 1.25 and an E. May do 1.25, pop up some zeros, maybe a very small times 10 or something like that. One of those things will probably happen at that point. Now, it's really important that when you hit your exponent button, you should not be hitting anything like the multiplication button. You should not be hitting anything like the second log button or inverse log button, because those are all wrong. When you hit that exponent button, it represents the times 10 part of the number, which means you don't need to hit the multiplication button. You shouldn't be doing anything with the log button if you're doing scientific notation in your calculator. So what's left is really just the exponent part that we need to put in there. That brings us to the 2 other buttons that are commonly found on calculators, and that's actually your negative button. And it usually is a button that looks something like this, or you may have a button that looks like this. It is not the subtract button, yeah? So not the subtract button. So at this point, what you would hit next is your negative button. and 4, and that will turn that into a -4. It'll turn this into a -4. And that is the proper way to punch scientific notation into your calculator if you would like to get the right answer, which I imagine you would. So that is definitely the button that you want to use. Now, if you do have this button or this combination type calculator, and once again, those are usually like two-tone calculators, like a main color and a sort of different color on the sides. You pretty much will do the same thing, except that typically speaking, the way those calculators are programmed, you got to put parentheses around every number in scientific notation. Otherwise, it will do the math wrong. So if you have this type of calculator, you would start with actually a parentheses. And then you would do kind of the same thing. You would do 1.25. You would then hit your exponent button. Again, no multiplication button, just your exponent button. And on your calculator, you will probably have something that looks like this, 1.25. It will pop a times 10. And then you'll have like a blinking little caret up here, a blinking box at that point. At that point, you can put the rest of it in just like normal. You would hit your negative button, whichever one you got, and 4. And then that will turn this into 1.25 times 10 to the -4. Your little blinking box will now be next door to it. Now, in my experience, most of the time, these calculators are also programmed pretty crappily, which means you need to fix that little box that's way up on top. It actually needs to come back down to a normal size. And that's where the wheel comes into play. You hit the wheel right there. You want to go and then hit the wheel. That will bring this guy back down. Now your box is back down, and now you can close the parentheses and you will finally be done there. So a little extra work, not a lot once you obviously get the hang of it, but you do have to put parentheses around all the numbers if you have that type of calculator, because again, it will pretty much do the math wrong if you don't do that. If you have the EE button, the EXP button, you can put as many numbers as you want with no parentheses. It's all good. You don't really have to be that careful. But if you have the other type, you do need to be really careful with it. This is definitely the way that you want to put a number in scientific notation in to your calculator all the time. You don't want to do any of those other common things that people do. Use like the shift, the log button, because it'll be wrong. How you know you're putting something in scientific notation wrong in a calculation is you'll see your answer looks really good at the beginning, but the exponent part's off by like 1 or so. And that's usually a result of you punching it incorrectly. So if you're not sure where your exponent button is, just at some point, bring your calculator up. We'll figure it out together at some point, and we'll be able to do that. Any questions on that there? All right, so I think, yeah.